This is the SeniorProject introductory video for Robotic Arm version 1 for Spring 2016. Team members are Curtis Cox and Shade Ferris Francis. Mentor is Dr. Nagarajan Prabhakar, and instructor is Dr. Masood Sajadi. The software solution for the Robotic Arm project will be discussed in this video. The Robotic Arm project is a branch within the Telebot project of Florida International University's Applied Research Lab, the Discovery Lab. In 2012, U.S. Navy Reserve Lieutenant Commander Jeremy Robbins donated $20,000 to the Discovery Lab for the creation of a telepresence robot to assist disabled police and military veterans in their return to the workforce. This robot, Telebot, provides a mode of remote law enforcement surveillance so that officers can patrol locations and interact with citizens in normal or emergency situations. The Robot Arm project is a subset of the third iteration of the Telebot prototype. The robotic arm subsystem demonstrates that the feasibility of creating a low-cost alternative to expensive robotic software and hardware solutions is possible. At the onset of the senior design portion of the Telebot project, Telebot arm operations were as follows. In earlier software designs, the crucial difference was a centralized architecture and communication through TCP/IP. This proved unreliable, since if the ARM subsystem were to crash, all other subsystems would follow and the entire system would have to be restarted. This prompted a switch to the publish-subscribe message passing and modular publisher-subscriber programs for the ARM and other subsystems on the operator PC and robot PC. To operate the robotic arms, the operator would secure the 3-space sensor IMU sensors along her hands, lower and upper arms, back, shoulders, chest, and head. As the operator moves her arms, data from the IMUs are transmitted to the motion capture software, the YEI 3-Space Mocap Studio. This software calculates joint data for the head, wrist, elbow, and shoulder joints of the left and right arms, which is locally transmitted via TCP/IP to a local master program. This master program then calculates servo motor position units and publishes this data to a topic or a message mailbox in accordance to the publish-subscribe protocol. On Linux-based Telebot, a slave subscriber reads the data from this topic and passes this data to the Robotis CM700 controller, which communicates with 6 daisy-chained Robotis Dynamixel servo actuators on each robot arm and 2 in the robot neck. These servo motors rotate to the position units given in the sent data, mimicking the arm movements of the operator. If the master or slave program is prematurely terminated, the other side will continue to publish data to the topic or listen for data from the topic without termination or interruption. The master and slave are unaware of the presence of each other, which is key to the reliable remote operation of Telebot. In this latest iteration of the robotic arm subsystem, 4 problems were encountered. Accurate mimicry of the operator needed to be achieved. The mapping formula used for joint angle to servo motor position needed to be adjusted for smoother robotic arm movement. Usability of the operator software required a steep learning curve. This would require hours of training to become familiar and comfortable with robotic operation. To fulfill the purpose of Telebot's creation, the potential for a variety of interfaces such as sensor-based or joystick-based control should be available so that officers with different disabilities can seamlessly switch devices in order to manipulate the robotic arms in a way that is suitable to their operational needs. Appropriate up-to-date software was needed to test servo motors without the need of the main control programs. To tackle these limitations, we proposed 3 solutions and a correction: the reassessment of the mapping formula using calculated quaternion angles, a more user-friendly interface and operation for the main control program, the IMU control system, an alternative mode of robotic arm operation using voice commands, and a servo motor test program to test servo motor positions. To tackle these limitations, requirements were collected from our product owner, Dr. Prabhakar, and members of the Discovery Lab. The requirements are as follows: activate DDS publishing when clicking Activate DDS button, display angular data received for each joint in the IMU Master Publisher GUI, process angular data to servo motor units with IMU Master Publisher program, connect mocap system to the IMU Master Publisher program, initiate mocap halt rest position, process commands to servo motor units with voice Master Publisher program, connect voice control system to Voice Master Publisher program, understand DDS message delivery, ARM servo test driver, monitor servo feedback, DDS servo correction, minimize servo feedback latency, improve the mocap algorithm, and develop ARM quaternion calculation algorithm. The GUI is designed for the Servo Tester application, IMU Master Publisher, and the Voice Master Publisher were simple, to-the-point layouts for the sake of eliminating previous complications with robot operation. An operator can connect to ports, activate publish-subscribe communication, or rotate servo motors directly without outdated programs or having to change values in code or monitoring consoles. The aim and continuous goal of the evolution of this implementation is to provide the user-friendliness and accessibility needed for officers with various physical abilities and operational preferences to utilize this law enforcement telepresence robot at their ease. The new software solution presented for the next version of the third iteration will provide the usability, accessibility, and more fine-tuned functionality needed to assist the Discovery Lab in deploying a field-ready version of Telebot.